Welcome everybody to Alvascience Webinar. Today's topic is molecular descriptors generation with alvaDesc. In particular, we are going to see the new features of alvaDesc version 3, which was recently released. Before starting, a couple of things. You can write your questions in the chat. If we don't answer immediately, we will try to address your question at the end of the webinar. This webinar session is recorded, and the recording will be available on our YouTube channel in the next few days. We invite you to check out our YouTube channel, which contains many videos about Alvascience software solutions. You can find the link to the YouTube channel and more information about our products on our site, alvascience.com. I leave the floor to you, Andrea.
Thank you, Matteo, and welcome to everybody. Thank you for joining today's webinar on alvaDesc, where we'll explore how to calculate molecular features, such as molecular descriptors, molecular fingerprints, and structural patterns. We'll begin by introducing alvaDesc graphical user interface, which also allows for preliminary data analysis. And then we will move on the command line interface and its integration with KNIME and Python environments. Before we start, let's place alvaDesc within the broader context of the QSAR workflow. This workflow generally comprises 4 main steps, starting with data curation. That is one of the most time-intensive tasks. Data curation is where you prepare and standardize your dataset, a process that can be efficiently managed with alvaMolecule, that is our tool for visualizing, analyzing, and standardizing molecular data. If you're interested in data curation, you can check our webinar on how to curate a molecular dataset using alvaMolecule that is available on our YouTube channel. The second step, which we'll focus on today, is feature generation using alvaDesc in order to calculate molecular descriptors, fingerprints, and structural patterns. After feature generation, you can save the dataset as an alvaDesc project, ready for the next step, that is model building and validation, which can be accomplished using alvaModel. Since alvaDesc calculates thousands of molecular descriptors, feature selection is a mandatory task to build models with predictive capabilities. So this task can be accomplished using alvaModel that can be used to select the optimal features to predict a defined endpoint. With alvaModel, you can build both regression and classification models. The final step in the QSAR workflow is the model deployment. Models built in alvaModel can be exported as alvaRunner projects. These portable project files contains everything needed to apply models to a new molecular dataset, making the possibility to share your models with collaborators or as, for example, supplementary material on your research paper, an easy task. So you can find a detailed webinar on model building and model deployment using alvaModel and alvaRunner on our YouTube channel. We've also developed alvaBuilder, that is a tool for de novo molecular design. alvaBuilder uses genetic algorithms to design new molecules with targeted properties. So now let's talk about alvaDesc's capabilities. alvaDesc calculates nearly 6,000 molecular descriptors with over 4,000 molecular descriptors that are independent from the three-dimensional structure of the molecules. These two-dimensional descriptors cover categories such as constitutional, topological indices, pharmacophore descriptors, and two-dimensional autocorrelation descriptors, and so on. alvaDesc also supports 3 molecular fingerprints that are the max 166 molecular fingerprint, the extended connectivity fingerprints, and the path fingerprints. Starting from alvaDesc 3.0, alvaDesc can also identify structural pattern occurrences within your dataset. As mentioned earlier, alvaDesc is available with both a graphical user interface and a command line interface. The command line interface can be easily integrated into KNIME and Python environments, and Matteo will explore these options later in this webinar. Finally, alvaDesc is available for Linux, Windows, and Mac. So thank you once again for joining, and let's get started. So we can launch alvaDesc graphical user interface, and we can start adding molecular files to our dataset. alvaDesc allows the loading of one or more molecular files, or we can just drag and drop our files into alvaDesc. alvaDesc imports the most common molecular file formats, such as CBIL, MDL, and SMILES file format, and can be used to merge different sources into a single dataset. In this case, let's load a single file, specifically a text file. When loading a text file, alvaDesc automatically detects the SMILES and name columns in the dataset. The text file must include a column including the SMILES representation of the molecule. In this case, alvaDesc automatically detected the two columns, the SMILES and the name column, but we could manually select the appropriate columns if alvaDesc do not recognize properly the SMILES and name columns. In addition to the SMILES and name columns, this dataset includes two additional variables, one indicating the biodegradability of each chemical, and another specifying the split between the training and the test set. This particular file represents the training set for a QSAL model designed to predict the ready biodegradability of chemicals, and these models are available for free on our website. So we have two values, RB in the class column, RB that stands for ready biodegradable, and NRB that stands for not ready biodegradable. And then we have two different values, training and test, in the training test column. alvaDesc can automatically identify and import any additional fields present in the source file. So let's go ahead and import these two additional fields. Once the data is loaded, all the molecules are displayed in a spreadsheet-like view. In the status bar, we can see some general information about our dataset. For example, we can see the number of molecules that have been loaded, that are 1,722 molecules, and the number of external variables that have been loaded directly from the source file. We can use the molecule spreadsheet for exploring our dataset. We can sort and filter the imported variable, and in order to sort and filter the variable, we can just right-click on the desired column header, and we can, for example, sort by name. We can filter only those molecules that belong to the ready biodegradable chemicals, and we can also check that we have 545 molecules that belongs to the ready biodegradability class, and we can also filter, make any filters, as many filters as we want. So we can also filter using the training test column. Oops, I typed wrong. So training, so we can see that we have 354 molecules that belongs to the training set and have a value of ready biodegradability for the molecules. In addition to the filtering on the imported variables, we can also filter on the calculated descriptors as soon as we calculate them. We can also filter our dataset using the molecule column. We can filter only those molecules that include or do not include a specific structural pattern. Structural patterns can be defined using the smart syntax. So let's, for example, look for oxirane substructure. So we have filtered our molecules showing only those molecules, including the oxygen substructure. So we can see that we have 8 molecules, including the oxygen substructure. So we have seen how we can use some features that we can use when dealing with the molecular spreadsheet. But before calculating the molecular descriptors, let's explore the main functionalities of alvaDesc graphical interface. We can start from the edit menu. Besides the basic functionalities, such as the possibility to copy the selected molecule in different formats, let's see how we can use alvaDesc to search for molecules in external databases like PubChem and Google Patents. These searches can be performed based on the full structure or the substructure or similarity, enabling to quick access additional information, or in case of Google Patents, patent data related to the molecules in our dataset. So we can look at these molecules. So we can alvaDesc automatically opens a web page including the selected molecule. So we are looking for this molecule in PubChem, and we can do the same using Google Patents and Scholar. So we can look for the whole molecule, or we can look for molecule based on similarity. Now let's have a look at the grid-related features. The molecules can be visualized both as a molecular worksheet or as a molecular grid. Filtering and sorting are preserved when switching between the two grid style, and we can switch between the worksheet and the grid using the grid menu or using the keyboard shortcuts. So in this case, on my Mac, the shortcut is Command D, while it's Control D on Windows and Linux. When the dataset is visualized as a worksheet, we can also use the column selection menu to select the visible columns. We have only 2 variables right now, the variables that we have imported from the source file, but this selection feature can be very useful after the calculation of molecular descriptors, when the visible columns can be thousands. So we have some other visualization options. Among them, we can show the atomic partial charges for our molecules, or we can highlight specific features of our molecules. For example, we can highlight a specific pattern specified by a smart string. Let's, for example, highlight the oxygen substructure. So you can see that all the oxygen substructures are highlighted in our dataset. We can also highlight the Bemis-Murko features of our molecules, Bemis-Murko features that are the ring systems, the linkers connecting the ring systems, and the side chains. Finally, let's show the molecule detail. In the molecule detail, we can find some specific information about the selected molecule. We can see, for example, the information about the number of implicit hydrogens, or the availability of 3-dimensional coordinates or atomic partial charges. If the atomic partial charges are not available in the source file, like in this case, where we imported molecules from SMILES, alvaDesc automatically calculates them using Gasteiger's algorithm for the calculation of atomic partial charges. So we've explored some of the basic functionalities of alvaDesc graphical user interface. Now let's move on the core functionality of alvaDesc, the calculation of molecular features. So let's start with molecular descriptors. And what is a molecular descriptor? A molecular descriptor is essentially a mathematical representation of a chemical structure. This representation translates the chemical information into numerical values or sets of values. And these values can be then used for further analysis, such as QSAR and QSPR modeling, exploratory data analysis, similarity analysis, and so on. alvaDesc is capable of calculating nearly 6,000 molecular descriptors, specifically 5,799 molecular descriptors. Over than 4,000 molecular descriptors are independent of the three-dimensional structure of the molecules. These, the descriptors calculated by alvaDesc are organized into 34 logical blocks, and this makes it easier to navigate and select the appropriate descriptors for your analysis. Some blocks, such as the topological indices or the two-dimensional matrix-based descriptors, are further divided into sub-blocks. alvaDesc calculates zero-dimensional, one-dimensional, two-dimensional, and three-dimensional molecular descriptors. Zero-dimensional descriptors are the simplest descriptors. They provide basic information about the molecular composition without considering the connection between the atoms. For example, they count the number of atoms, the number of bonds, or specific atom types. alvaDesc calculates the constitutional descriptors that belong to the zero-dimensional descriptors, and we can find the molecular weight, the calculation of specific atom types, or the percentage of specific atom types. Then we have one-dimensional descriptors that represent the molecules as collection of substructures, such as functional groups or atom-centered fragments. So let's have a look at the functional groups. For example, alvaDesc includes 154 functional groups that can be counted in your molecules, and we can find that there are a lot of substructures in this type, in this logical block, as well as in the atom-centered fragments. They are all one-dimensional descriptors, since they are just substructures that are counted in the molecule. We have then the two-dimensional descriptors that look how the atoms are connected in the molecule in terms of both presence and nature of chemical bonds. So they usually the molecules is represented as a chemical graph, whose vertices are the atoms and edges are the bonds. The bonds are considered with respect to their nature, so they can be differentiated among single, double, aromatic, and triple bonds. Two-dimensional descriptors included in alvaDesc are, for example, the topological indices, the walk and path counts, connectivity indices, two-dimensional autocorrelations, and so on. Finally, we have the three-dimensional descriptors that add the information about the three-dimensional arrangement of the atoms in the space. These descriptors require the three-dimensional coordinates of the atoms, and alvaDesc calculates various types of three-dimensional descriptors, such as the geometrical descriptors, WIM and gateway descriptors, and solvent-accessible surface area descriptors. Each type of descriptors, 0D, 1D, 2D, and 3D, adds a layer of information, allowing you to analyze your molecules from different perspectives. If you need to calculate specific descriptors, you can use this interface to find the descriptor you're looking for. You can also filter the descriptors based on the descriptor symbol or based on the descriptor description. There are few options in order to better select the descriptors you want to calculate. In this case, let's calculate all the descriptors that are included in alvaDesc. Since we have loaded a SMILES format, so the coordinates are not available in the source file, alvaDesc asks us if we want to calculate only the two-dimensional descriptors or if we are interested in calculating the three-dimensional descriptors. Since alvaDesc 3.0, alvaDesc provides the functionality to calculate the three-dimensional coordinates of the atoms in your molecules. The three-dimensional coordinates are calculated using a distance geometry algorithm followed by force field optimization. So alvaDesc is currently calculating the coordinates for all the molecules. We can see that the molecules are already represented in a three-dimensional way. So anyway, let's remove the highlights and the atomic partial charges. So we can see the our data that so our molecules that are represented in a three-dimensional way. All the three-dimensional coordinates for our data set have been calculated. So we can now calculate all the descriptors, all the 5,799 molecular descriptors. As you can see, the status bar is updated. So now we can see that the three-dimensional coordinates have been calculated, and we can see the same in the molecule detail of our molecules. So let's switch to the two-dimensional representation of our molecules. So now we have calculated all the molecular descriptors. So we have seen how to calculate molecular descriptors. Let's see how to calculate molecular fingerprints. alvaDesc provides two different types of molecular fingerprints: extended connectivity fingerprints and path fingerprints. Since alvaDesc 3.0, we introduced a new implementation of the extended connectivity fingerprints that is faster than the previous one and can be used to add additional information when you calculate the fingerprints that were not available in the previous version. With the new version of the extended connectivity fingerprints, we can take into account also the presence of isotope and the stereochemistry. But anyway, let's have a look at the options for the calculation of molecular fingerprints. We can define the size of the fingerprint. Since the fingerprint is a sequence of 0 and 1 values, and it has a fixed size, we can define the size of the fragments that we want to evaluate during the fingerprint calculation. We can select this option, that is count fragments. If this option is enabled, the fingerprints will take into account the occurrences of every fragment in the molecule. So if the same fragment occurs more than one time, the fingerprint will be able to take into account the presence of multiple occurrences of the same fragment. Let's see the atom options. We can choose how we want to represent the substructure that are identified during the fingerprint calculation. For example, when the isotope option is enabled, substructures are encoded by taking into account the isotopic masses of the atoms. This means that two substructures composed of the same atomic types but with different isotopic masses will be assigned to different bits in the fingerprint. Conversely, if this option is disabled, atoms are not distinguished based on their atomic masses. So it's up to you if you are interested in discriminating molecules with respect to the isotopic information, the stereochemistry information, the formal charge information, and so on. So let's calculate the molecular fingerprints. It's really fast. After the calculation, we can see some statistics about the calculated fingerprints, the options used for the calculation of the molecular fingerprints, and some information about the density distribution, so the distribution of 1 and zeros in the molecular fingerprints. We can save both the statistics and the fingerprints as a text file. Let's now calculate the max 166 molecular fingerprints. The max 166 fingerprint is a fixed size structural key consisting of 166 predefined molecular features. Each bit in the max fingerprint represents the presence or the absence of that specific molecular feature. while the extended connectivity fingerprints that we have seen before are hashed fingerprints. So every bit in the fingerprint that does not necessarily reflect the presence of a specific fragment, but eventually it can reflect the presence of one or more fragments, since we have the so-called bit collision. So even for the MAX 166 fingerprints, we have some basic information about the distribution of the fragments that we have identified in our molecular dataset. Like for the hashed fingerprints, we can save the MAX fingerprints in a text file. In addition to the calculation of molecular descriptors and molecular fingerprints, starting from alvaDesc 3.0, it is possible to calculate also the occurrences of user-defined structural patterns. We can define the patterns that we want to find in our dataset using the SMART syntax. We can define very simple smarts. For example, capital A stands for aliphatic atoms. We can define both the pattern and the name of that pattern. We can then add additional patterns, for example, aromatic atoms, or even more complex patterns, such as, for example, in this case, the oxirane substructure, or, for example, the benzene substructure. We can define the substructures that we want to find in our dataset. Then we can define some options in order to identify the structural patterns. And one of these options is the count structural patterns occurrences. If this option is selected, the structural patterns will be identified and counted. If this option is not selected, if a structural patterns appear in a molecule, independently on the number of occurrences, the corresponding variable, so in this case the aliphatic atoms, for example, if we have just one or more aliphatic atoms in our molecule, if we don't select this option, we will have a column of 0 and 1, 0 if the substructure is not present, 1 if the substructure is present, while if we select this option, we can count the occurrences, so how many aliphatic atoms are present in our molecule. We can have an additional option that is the test smarts. This can be used to evaluate your smarts in order to check if they properly identify the molecules we are looking for. For example, let's see if it properly identifies the benzene ring independently of the benzene representation. We wrote the SMICE using the KQLA format, the KQLA representation of the benzene. The alvaDesc automatically identifies these the benzene in this structure, in this molecule, independently from the representation. So we can use this tool to check the smarts that we are looking for. It's very useful if we have complex smarts that we want to identify. In this case, we have very simple smarts, so it's quite simple to identify that these smarts are correct or not. So let's calculate the structural patterns. After the calculation of molecular descriptors, and structural patterns, all the columns are added to the molecular worksheet. So now we have almost 6,000 columns, and we can use the column selection tool to select which column we want to show in our molecular worksheet. So we've explored some of the features of alvaDesc graphical user interface and covered the calculation of molecular features, including molecular descriptors, fingerprints, structure patterns. Now let's take a closer look at the preliminary data analysis capabilities that are available in alvaDesc. alvaDesc provides a set of functionalities that can be used to analyze the calculated data. We can, for example, evaluate the univariate statistics of the calculated molecular descriptors and patterns. So we can evaluate some basic statistics of our molecular descriptors. We can filter them and we can check them. We can also evaluate the correlation, the Pearson correlation among the calculated descriptors. We can calculate the correlation using all the descriptors or a selection of the molecular descriptors. For sake of simplicity, let's select just the constitutional indices and the molecular properties. So we can see the correlation map showing the pair correlation among different descriptors, any pair of the calculated descriptors. And we can also evaluate the correlation of a single descriptors among all the others. Let's now explore the principal component analysis functionality that is available in alvaDesc. Principal components can be calculated on descriptors and on the fingerprints, both max fingerprints and extended or hashed fingerprints. So on every features we have calculated. PCA, in a way, is a technique that is used to reduce the dimensionality of a data set by transforming the original descriptors into a smaller set of new variables that are called the principal components. These principal components capture the most important variance in the data. So let's select, like for the correlation analysis, the constitutional indices and the molecular properties. When performing the PCA in alvaDesc, you can see two different plots that are displayed side by side, the loading plot on the left side and the score plot on the right side. Let's hide the molecule detail in order to better evaluate the plots. We can also hide this interface that can be used to select the variables that are shown in the plots, so the different principal components. And here we can find also the information about the explained variance of the single principal components. Anyway, we have the loading plot on the left side that shows how the original descriptors contribute to the principal components, indicating which descriptors are most influential in differentiating the molecules. So we can see the symbol of each descriptors and their contribution to the two selected principal components, in this case, the first and the second principal components. On the right side, we have the score plot that represent the molecules in the reduced dimensional space. Each point corresponds to a molecule, and its position reflects the selected principal component. This plot can help in identifying clusters, patterns, or outliers. So we can see, for example, that we have some molecules that are quite far from all the others. They are, in effect, quite different molecules from the rest of the data set. We can also evaluate how the molecules are distributed along the two principal components. We can, for example, see that we have on the left side of the score plot generally small molecules, while moving on to the right side of the score plot, the molecule size and complexity increases. And we can also check that starting from the bottom side of the score plot, we have molecules with many rings, while going up to the top of the score plot, we can find a lot of molecules that are linear or quite linear with just some branches. And these can show how principal components can be useful to discriminate and to explore our data set. We can also use the additional this interface to show additional information in our data set. For example, we can use the possibility to colorize the items in the score plot using a specified column. For example, we can use the class column, and we can see, for example, the distribution of the ready biodegradable and not ready biodegradable chemicals in the score plot, including the first and the second principal components. And we can see that mostly all of the linear compounds are considered ready biodegradable, while complex compounds are mainly not ready biodegradable. We have seen also that along the first principal components, we have an increase of the size of the molecules. We can, for example, highlight this using the size option. We can draw the points size reflecting a specific descriptor, in this case, the molecular weight. So we have taken a brief look at the data analysis functionality included in alvaDesc. To wrap up our overview of alvaDesc graphical user interface, let's explore the available charting options. alvaDesc chart types are histograms, bar plots, and scatter plots. Here we have the bar plots. We can see the histogram of a specific variable, of a specific descriptor. We can choose the number of bins in order to show specific representation of the considered molecular descriptor. And we can also have a look at the scatter plot. In the scatter plot and in all the plots provided with alvaDesc, we can select specific items by clicking or by selecting a region, using both a rectangular selection or a lasso selection. So we can, for example, select this portion of molecules. So this one. So we have selected 13 molecules. We can still filter and select the molecules also using the molecular grid. And the selection, if we select, for example, only those molecules that have a molecular weight greater than 200, we can see that in gray, we have the molecules that are not selected by the grid, so that are not visible in the grid, and in green, we can see the selectable molecules. These charts provide a flexible way to explore and visualize your data set. And so we are approaching the end of the graphical user interface presentation. But before letting the floor to Matteo, let's have a look on how to save the calculated data. We have already seen how to save the molecular fingerprints. So let's have a look on how to save molecular descriptors. We can see the usual molecular descriptors selection interface. So we can select only the descriptors that we want to save. We can also decide to save all the molecules that are included in the dataset or only the filtered ones. So in this case, we have only just 13 molecules that have been filtered. So let's save just the filtered molecules. Since we calculated a lot of descriptors, alvaDesc asked us if we want to reduce the number of descriptors to be saved. alvaDesc shows an interface where we can select the descriptors that we want to exclude from the saving. For example, we can exclude the constant values, the constant descriptors. We have more than 1,000 descriptors that are constant. So let's go ahead. We can save the molecular descriptors in different file formats. The usual text file, tabulated text file, where we have a column for each molecular descriptors. We can save the molecular descriptors in the smiles file with header, that is a specific text file including an header and where the first column must include the smiles. We can also save the molecular descriptors in an MDL file format, so every molecule will have its descriptors, and we can also save the molecular descriptors in as an Excel file. So let's see how to save our descriptors in an Excel file. Since saving the images can be time demanding, if we have a lot of molecules, this is not the case. It's not the case even for 1,000 molecules or so on. Anyway, we can save the images, so the text file with the images. So let's have a look on how the Excel file looks like. So we have the first column including the images of the molecules, and then we have all the molecular descriptors, including the name and the smiles. Finally, we can save the molecular descriptors, including the full data set, the molecules, and the molecular fingerprints, and all the features that we have calculated as an alvaDesc project. The alvaDesc project includes all the information that are included in our data set, so the molecular structures and all the calculated features. The alvaDesc project can be reopened by alvaDesc, so we can add more descriptors, or we can add more variables, or add more molecular fingerprints with, for example, different options selected. And the alvaDesc project is also the starting point for the model building and validation step that can be performed using Alva model.
Thank
Matteo?
you, Andrea.
Okay, I'll
share my screen. Okay, perfect. So what we saw so far was the use of the graphic user interface of alvaDesc. Particularly, Andrea was on a macOS computer. But alvaDesc is provided also as a command line interface that can be used on all three operating systems. For example, you can use directly the command line interface on a DOS prompt on Windows, on the terminal on macOS, or on a bash shell in Linux. Today, we won't see the direct use of the command line interface. Instead, we're going to see how the command line interface can be integrated into tools, KNIME and Python. Let's start from KNIME. KNIME is a very well-known platform for data science. It's structured as a visual workflow composed by nodes. Nodes are the building blocks of KNIME that can be used to import data, to manipulate it, to generate data, or to export data. In order to use alvaDesc inside KNIME, we need to have alvaDesc installed on the same computer. And we need also to install a plugin that was developed by us, a KNIME plugin that can be installed following standard KNIME procedure. To find such instructions, you can go to our site where you can find both the text description of the installation procedure, but also a video showing how to perform the installation. Also on our website, you can find a similar example of the workflow we're going to see today that can work as a starting point to use alvaDesc within KNIME. The plugin is characterized by three major nodes, one called Descriptor to calculate molecular descriptors, one called Fingerprint to calculate fingerprint, and one called Pattern to calculate a structural pattern defined as smart strings. Let's have a look. First, I have to tell you that all three nodes can read molecules either using a fourth node distributed with a plugin called Molecular Reader, or using standard KNIME nodes, like, for example, the SDF reader, which is a standard KNIME node to read files in SDF or MDL molecular file format. Or, for example, in this workflow example, we can see the use of the file reader, which is a standard KNIME node used to read text files, but this node is also is capable to handle molecule defined as a SMILES format, as we can see here. Let's have a look at the configuration of the descriptor node. The first important option is the definition of the path of the alvaDesc command line interface. It's an executable called alvaDescCLI.exe in Windows, of course. The path is dependent on where you installed alvaDesc, but also changes, of course, depending on the operating system you are on. The next important option is the multi-threading option. This is a new option. Is only available when using alvaDesc version 3. We invite you, if you have alvaDesc 3, to turn this option on, because it can significantly improve the speed of molecular descriptor calculation inside the KNIME. Then we have a few input-output options. For example, we have the possibility to define the name of the column in the input table that contains the molecule, and which format to use to interpret the molecules. We have serial MDL SMILES, or we can leave it to automatic detection. And finally, an option that allows us to decide if in the output table the input column should be included or not. In the descriptors tab, we can select the blocks of descriptors we want to calculate. By default, they are all selected. And in the calculation tab, we have a set of options related to descriptors calculation. These are options that are similar to the one you can find inside alvaDesc. Let's execute this node. We can check the output table. We can see that the table contains for each row a molecule and the related name and descriptors that were selected to be calculated. As it's normal for a KNIME workflow, you can then use this data in the rest of your workflow. In this simple example, we're going to just simply write it in a CSV file. Let's have a look to the configuration of the fingerprint node. In the first tab, we have exactly the same option. And then we have a fingerprint tab that allows us to select which fingerprint we want to calculate and some options related to the fingerprint. These are basically the options that Andrea showed us inside the graphic user interface. We can execute this node as well. Finally, the pattern node, as you can see, takes two input. One, again, are the molecules, and the second one is the definition of the pattern, the structural patterns that we want to identify. These patterns must be defined as shown in the graphical user interface before as smart strings. In this case, we used a standard KNIME node called table creator that allowed us to define a simple table where in one column we define the smarts that we will use. The options of the pattern are similar. They are similar, but we also have an extra input column name, which is the one that defines the smarts. In the pattern tab, we have similar options to the one we saw before. In particular, we're going to select count structural patterns occurrences. We can execute even this node. And similarly to the table structure we saw before, in each row we have a molecule, and we have all the columns related to the patterns that we selected. Okay, that's it for KNIME. Let's have a look at Python. Similarly to what we saw in the for KNIME, we developed a library in Python called alvaDescCLI wrapper, which allows us to integrate the use of alvaDescCLI inside Python. For the installation of such library, you can always check our website, and even in this case, there are instructions on how to install, but there's also a video showing how to install the library on your computer. Such library should work with every Python environment. In this specific example, we are on Windows. This is Visual Studio Code with an integration of Python inside the Visual Studio Code. Even this example is available in the documentation provided with the library. In the first part, we will include all the necessary libraries, of course, the alvaDescCLI wrapper, and also we're going to use pandas. And we're going to init the alvaDesc option. Even in this case, we have to specify where the alvaDescCLI executable is. Let's execute this part. In this example, we will load a bunch of molecules expressed as miles strings and passing that to the alvaDesc object. And we're going to calculate some descriptors. We could have calculated them all, but in this case, we only selected a few. Also, we're going to calculate the structural patterns expressed as smarts. And we're going to take this output and put them together in a pandas data frame. Pandas data frame, which is a very popular library in Python to handle data. We therefore created a pandas data frame called df, and we're going to look at it at the first 10 lines using the head command. As you can see, we have a table similar to the one we saw before, where each line corresponds to a molecule, and then we have the column of the selected descriptors and patterns. That's it for also Python integration. Andrea, you are there?
Yeah, I'm here. I don't see any question about KNIME and Python in the chat.
Okay, do you want to share your screen?
Yeah.
I will start saying that since someone was asking again, that this recording will be available in the next few days on our YouTube channel. In general, I wanted to invite you to get in touch with us. You can do that through our site where we have a contact us form, or if you already are in touch with us, just send us an email. I wanted to answer to one of the questions I saw in the chat right away. One question was, I have alvaDesc 3.0. Do I have all these options? The answer is yes. If you have a license of alvaDesc, you have a functioning alvaDesc 3.0, you have all the functionalities we showed you, and also you can use the command line interface also integrated in KNIME and Python. Andrea, there is a question you might want to answer related to fingerprints.
Yeah, I saw it related to the possibility to identify the bits and the corresponding molecular features. Is that
exactly?
Regarding max, yes, every column is reflects the presence of a specific substructure, while using the hashed fingerprints, such as the extended connectivity and the path fingerprints. Every bit in the fingerprints does not reflect necessarily one single substructure, but even more than one substructure. And also, you can define to switch on more than one bit to when identifying one single structure. So currently, it's not possible using alvaDesc to put in relation the bits in the hashed fingerprints and specific substructures, but it's something that we are considering it for future releases.
Okay. Another question was, is it possible to add more than one pattern at once?
Yes, okay, I saw that question. Yes, it is possible. For example, we have here a set of smarts. Okay, these smarts are quite complex, as you can see, and we have just two columns. The first column is a text file with two columns. The first column is the smarts, the second column is the name, but we can just have one column, including the smarts, and we can directly paste in the structure of pattern interface. So we have the fourth pattern already calculated. We want to add these patterns, so we can just click and paste. We can just paste the patterns, and we can see that all the patterns are added to the structure of patterns, and we can calculate them onto the whole dataset. So yes, it is possible.
Okay, thank you. One final question is related to the smart syntax, where we can find more information about them.
Okay. Okay, smart syntax is a syntax developed by Daylight, by Daylight, sorry. And anyway, in the alvaDesc documentation, alvaDesc is provided with the full documentation, with a detailed documentation, including also the information about how the smarts are defined. So you can find a proper chapter describing the smart syntax, but you can also find the link to the Daylight Chemical Information Systems website, where you can find additional information about the smarts representation. But anyway, here you can find all the information about the atom primitives, bond primitives, how you can define recursive smarts grouping, and you can also find some example. I take this opportunity to say that alvaDesc is provided with a detailed documentation, not describing only how to use alvaDesc, so how to calculate molecular descriptor, fingerprints, three-dimensional coordinates, how to use the command line interface, and so on, but it also includes the information about all the calculated descriptors. So, for example, you can find all the formulas used for the molecular descriptors calculation and a detailed bibliographic reference at the end of every chapter in the documentation. So I hope I answered these two questions.
Yes.
There are any other questions?
No, I wouldn't say that. And I guess we reached our deadline. So I would invite again everyone to get in touch with us through our site, alvascience.com. Thank you again.
Thank you again to everybody, and see you at the next webinar.
Okay. Bye-bye.
Bye.